Liquid in glass thermometer, it remains the most widely used type of thermometer, e.g. your clinic thermometer and the minimum and maximum thermometer. The range of the thermometer lies between 35 degrees Celsius and 45 degrees Celsius. As the normal body temperature of human body falls in between that range, it consists of short tube and narrow bore. Now we are looking at the principle, the mechanism behind your liquid in glass thermometer, how it works and how it functions. He said it consists of short tube. Do you understand? That's the short tube where the mercury is actually being located. Are you getting it? If you have this short tube, now the scientific aspect is here. Are you seeing it? Now this short tube is where your mercury is located. Now at this junction, we have the calibration. Are you seeing it? So this is the calibrations. Are you seeing it? Now if you check out the working principle, now it said contains the short tube and the narrow bore. This is the bore, this is the short tube. Now if you proceed to record the temperature of a person and the thermometer is placed under the tongue or under the armpit. Those are the major ways by which you can actually make use of your thermometer. Now for your gas thermometer, constant volume gas thermometer is an example of your gas thermometer. You can see the diagram there. Now the gas thermometer is basically used for very accurate temperature measurement. The operation utilizes the fact that its temperature changes for a large volume change of gas thermometer. It is also made up of large glass tube B containing air, and it is connected by a capillary tube to the mercury. You understand? Mercury manometer. So the way a glass thermometer functions is different from the way your clinical gas thermometer, your clinical thermometer functions. Your gas thermometer functions are more accurate, or gas thermometer measurements are more accurate than is your clinical gas thermometer. Now the right side of the AC of the manometer is moved up and down in order to bring the mercury on the other side of the original position. You can see the graph and the tables there that actually analyzes the working principle gas thermometer. The next one is your resistant thermometer. Very easy. It's a very good example of your resistant. If you look at it, the working principle there as in the thermometric substance there is your resistance in the wire. You can see the resistance circuit. It is resistance circuit that actually brings about that measurement of thermometer that is being felt. You understand? Look at the statement. It said it's a very good example of resistant thermometer is platinum resistance thermometer. Do you understand? An example is a platinum resistant thermometer. The thermometric substance used in this type of thermometer is the resistance of the platinum wire. Are you seeing it? That resistance experience there is what is actually bringing about the thermometric measurement. Now the working principle is based on the fact for a metallic conductor. Now the electric resistance changes proportionally with its temperature. So those are the major working principles of your resistant thermometer. So if we proceed, you obtain, you discover the temperature scales which I drew there. Have you seen it? So those are the major scales. This is your Fahrenheit scale, and this is your Kelvin scale. Have you seen it? So if you have these three scales, what you need to do is that if you are being given some question, for instance, if I decide to say, okay, convert 50 degrees Celsius to Kelvin. No, ideally, I'm supposed to just go to my equation, my normal equation, T equals 273 plus the degree Celsius value, which is 50. But if you don't want to use this, probably you forgot to remember the formula. Just come here. This is what you do. Oh yeah, let's go. 0 minus this, theta minus 0, all over 100 minus 0, settle. You come here, theta, let's say you want to convert to Kelvin. That would be 0 Kelvin minus 273, all over 373 minus 273. What am I doing? You relate any of the two scales. We are relating this and this now. This subtracts this, and the upper one too subtracts this. This subtracts this, and the upper one subtracts this. So by the time you do all that, remember, this is what we are looking for. So let's just put K here. So if this is 50, so it becomes 50 minus 0. That's 50 over 100. Right? Now from here you have 273 over this minus this will give you 100. So when 100 cancels each other, your K becomes 50 plus 273, which gives you 323. Correct? Yeah, which gives you 323 Kelvin. You can see, even if you now want to use your formula, you still obtain that particular value. So you can actually make use of this change of scale for you to obtain any value. So based on our analysis, you can see the three scales that was drawn, how to actually relate them: Celsius scale to Fahrenheit scale to Kelvin scale. Now, molecular explanation of temperature. Let's talk about that. Molecular explanation of temperature. We have what we call how you analyze the molecular structure, the molecular explanation of a particular temperature. Listen to the statement. It says the molecules that makes up a solid vibrate about a particular position. The molecules that makes up a solid vibrate about a fixed position. Now, when heat is applied to the solid, the amplitude of the vibration of this molecule begins to become larger, and invariably their kinetic energy increases from the kinetic theory. What are we saying? Very easy. This is your body. Now, there are some molecular structure, molecular arrangement of the atoms. Are we getting it? Now, when heat is applied, it tends to what? Boils in between these molecular structures. Now, when it boils, the level of their vibration will go much higher. Do you understand? When the vibration goes higher and more hot, you realize that they tend to what? They tend to, from that statement, you realize that the amplitude of vibration of this molecule becomes larger, and invariably their kinetic energy increases. So when the amplitude becomes larger, kinetic energy increases. Are you getting it? So from there, you'll be able to decode that it is the heat that is being applied here that increases the what? The vibration gap, and from there, it increases the kinetic energy. Are we getting it? Now, the total translational kinetic energy of the molecule is directly proportional to the absolute temperature. Are we getting it? Hence, increase in kinetic energy implies increase in the temperature of the molecule. That is just the molecular explanation of temperature. If you can get those four statements, the first one, the second one, the third one, and the fourth one, you are good to go. You've already explained what is meant by molecular explanation of what? Of your temperature. Now, let's go to the exercises. Mercury is brought to water as a thermometric liquid because A. Mercury has a lower boiling point. No. B. Mercury has uniform thermal expansion. C. Mercury has a lower coefficient of expansion. D. Mercury does not wet glass. That's the best option. Mercury doesn't wet the glass. Let's check number 2. Convert minus 10 degrees Celsius to Fahrenheit. A. 40 degrees Fahrenheit. B. 50 degrees Fahrenheit. C. 14 degrees Fahrenheit. D. 28 degrees Fahrenheit. How do we do that? I told you, you must draw your scale. For your Fahrenheit, we have what we call 32, and this is what we call 212. Here we have 0, and here we have 100. So if from there you have your x value. So for you to obtain it, what do? You just say your x minus 32, 2212 minus 32, right? If I'm correct from that angle, realize that our scale, we said for your Fahrenheit scale, we have your 212. Now, if we proceed, you discover that the upper fixed point of this is 100, the lower is 0. So by the time you start obtaining your values, it's going to be 10 minus 0 all over your 100 minus what? 0. So by the time you compute this, you are going to have x minus 32 all over your 212, 312 is 0, 11 minus this, you have 8, you already borrowed 1, you have 180. So you put your 180 here, then you have 10 over what? 100. So 0 cancels 0, 0 cancels 0. So you'll be able to have x minus 32 equals your what? 18. So from there you have the x equals 18 plus 32. You have 0, this is 50. So 50 degree Fahrenheit. Are you seeing it? So that will be 50 degree Fahrenheit, and that will be in option B. Option B. The third question says a thermometer has a stem mark in the multimeter instead of degree Celsius. The lower fixed point is, listen to this one, it's also another very it's an SSC question, another very technical one. You need to understand it properly before diving into it. What do I mean? You have to draw out your scale. You have to draw out your scale. Remember, Look at that question. It says the lower fixed point. You know, we are given another scale entirely. Now on that new scale, the lower is 30 millimeter. The higher is 180 millimeter. Are you seeing it? Now it's now being compared to a degree Celsius. They now say the temperature in degrees Celsius when the thermometer is 45 mm. So you are told to calculate the x in degrees Celsius. Upper for degrees Celsius is 100 0. Upper to lower. Lower is 0. Upper is 100. Now you are told to look for the equivalent degrees Celsius for what? 45 mm. What do? Do the way we, you know, just use this to subtract it. Then this minus that will be 45 minus 30. Then over 180 minus what? 30. You have your normal one, x minus 0 over 100 minus 0. If you subtract this, you are going to have 15 all over 150 equals x over 100. So 0 cancels 0, right? So you're going to have your x to be 15 times 10 all over 15. So when you cut the two, you're going to have 10 degrees Celsius. So the equivalent here is what? 10 degrees Celsius. Very easy. As you can see, it's an SSC question and it's being solved in 2 minutes. Number 4, distinguish between heat and temperature. You said that before. Now, a mercury in glass thermometer reads this at fixed point and this at steam point. Are you seeing it? Now, calculate the Celsius temperature corresponding to 70 degrees Celsius. If you look at it properly, mercury in glass, two scales are actually being analyzed there.